From the previous video, we show you the conditional probability. Like we say, conditional probability, we have original probability. For the example, we have second year and the third year. So then we told you more information about that. So that's why the probability changed. To solve this problem we showed you earlier, we can make the table to list all the second year students, then including list all the second and the third year students, then including their declared major or not. Then we can find the probability if we pick up student at random who is declared the major. That's one way to do. But a lot of time we can do is we use the Bayes rules. So the Bayes rules is very popular rule for the statistics and the data science. So what is the Bayes rule? The Bayes rule, the most important thing, we update your prediction based on the new information. So that's we say you have original condition about your situation, about each event, about their probability. But then we add more information on that. So that's why the whole events become multiple stage. So that is a multiple stage experiment. According to the new information adding, the chance of an event at early stage, they may change later on the probability for the later stage. So that we use the Bayes rules. We keep updating our probability. So that's why your so that's why we don't call events, because event we focus on the specific one event, we have their probability. So that's why here just say we have the experiment or the sequence event. They have multiple stage according to the new information added into there. Okay, so then the probability changed. So then we can find the chance for the event at the earlier stage. Then we will give the result to the later stage. So you can see the picture here actually is in the Big Bang theory. Then the Shelton did talk about the conditional probability. So that's why we show you this picture here. Okay, but let's continue to see using our example how we will do the Bayes rule to find our probability. So that's here we use for the Bayes rule. So since we have multiple stage of our probability, so that's why we just continue to make the tree diagram. Okay, so that's here. Remember the first beginning we told you in the class, we have 60% is the second year student, then 40% is the third year student. So that's our probability. Then here is our first stage, or we say the initial stage. Or here they say the prior probability. So here, of course, the 60% is for the second year. Then 40% is for the third year. So then continue in the example we told you. That's the first bullet, right? Then we told you the second bullet. For the second year student, we have 50% declare their major and 50% not declare their major. Then for the third year student, we have 80% declare their major and 20% not. So add more information. We just need to continue to add to new branches into our tree diagram. So that's earlier we say second year they have 50% declare and 50% not declare. Then third year student, we have 80% declare, 20% not declare. Okay, so what did you find? Right, and actually every time when we branch out, each set of the new branches, they add to 1. Okay, so when we have the new information added on, we just continue to add to our tree diagram. So this one we call that's the prior probability, or we say the stage 1. So then we have the new one. Okay, so that's our second stage. Or we can say that's the second stage, or we say the likelihood, or we say the conditional probability, because according to the new condition, then our probability changed. So according to this tree diagram, can we find the chance if we pick out a student, this student declared the major, what is the chance this student is the second year? And what is the chance this student is the third year? Right, we can, right? So actually here what we do is, since we told you we pick out the new student, we random pick out a student, they declare the major. So we only focus on the major being declared. So that's why we ignore the undeclared major. So from this declared major student, they can be from here. They can be second year. So if they are from second year, they are 60% times 50%. Why times? Because they are second year and declare the major. When we hear the and, we multiply. Again, it's not the only one, right? Of course, here is we try to find the probability the student is second year and declare the major. So that's 60% times 50%. But the whole population about the declared major student is what? So that's why we need to add this part and the third year part. So the third year students, you have 40% times 80%, they declare the major. So we add together, that's our denominator. So then here is our numerator for the second year. So after you calculate, right, you will see that's about 48%. That's the same as earlier we did in our demo file. Or we can go back to our demo file. Okay, so here we will have our tree diagram calculation. Okay, so this one will only focus on the second year student. So that will be 60% times 50 and divide by the whole student declared the major. So then you can compare, the answer is the same. So of course, if you want to do, you also can use this one. This tree diagram, we also can find, so what is the chance the student is third year and declare the major? So you can try to, using this one to calculate, to check your answer. Check your answer with your classmates. You can either just write a new cell in the Jupyter notebook or just using your calculator. Okay, so after we understand this tree diagram, how to build this tree diagram, so now let's go back to our clinical test exam. That's example. Okay, so this example, like earlier we say, right? So the same thing, we can build our tree diagram. Okay, I think let's go back to see the question again. So we go back to see the question again, so you will have better idea how we build a tree diagram. Okay, so here we just say, actually we have 1 out of 1,000 chance, so for that disease. Okay, so what we can do is, right, we can have 1,000 patients, but only one patient has that disease. Okay, so then you have the false positive rate for 5%. That's me. The person didn't get the disease, but the test result is 5%. Okay, so then we want you to try to find the chance the person find to have the positive result, and actually do have the disease. Okay, so then here you can back to see how the tree diagram came from. So that's what we see here, right? So that's why beginning you need to have what? We have the people with disease or without disease. So since earlier we told you that's 1%. 1 out of 1,000. So that's why you have about 0.1%. That's 0.001. They have the disease. But 0.999 is without disease. Okay? So then we told you, right? So you don't have disease, but once you do the testing, right? You either test positive or negative. And we did tell you, you test positive falsely is 5%. So that's why here we have the 5%, even you don't have that disease, you test positive. On the other hand, like earlier we said, right, all the branch, they add to 1. So the other branch without disease and test negative will be 0.95. Okay, so one thing is that we're looking for. Actually, we're looking for the people has disease and test positive. Okay, but here the problem didn't give us the true positive rate. So that's we call the true positive rate. That means you have disease, then you test positive. So the false positive means you don't have disease, but you test positive. So since we don't have this information, we just assume on the people with the disease test positive is 100%. So that's how we update our tree like this. Okay, so here we will make that 100%, and then here will be 0. Okay, so again, that's we said earlier. So that's the false positive, this true positive. So we assume the true positive rate is 1. Okay, so then, yeah. So I think here is the final tree look like this. Okay, so since we have 1 and 0, yeah, just quickly update here. So since we assume that will be the true positive will be 100%, so here is the 1. Then test negative is 0. Okay, so now we can go back to our question. Our question we ask you is, if a patient do have the disease and test positive, what is the chance? So that's why here we only care is what? We only care about the test positive. We want to know what is the percentage here. But this one is not enough because we know they had the test positive, but they can be with disease or without disease. So we need to consider this part and this part. So that's here we're looking for. Okay, so we're looking for the test positive, but they do have the disease. So then we need to multiply this branch. So we're using the 0.001 times 1. Okay, that's the numerator. But the denominator, we need to have both. So that's why we have 0.001 times 1 and 0.999 times 0.05. Okay, so then we got our percentage. So that's about 2% only. So did you get that right? Okay, of course, let's back to see our demo. So here, let's see this one first. Okay, so this one is earlier we see we apply the base rule and got the test positive and with the disease. So we need to use that in the numerator. Okay, so then the denominator we just divide by the test positive with the disease and the test positive but without disease. Okay, so that will be the result we have. It's about 2%. But this one, of course, we still can make the table like that. So that's why earlier at the beginning for this lecture file, we create a function called create population. You specified the chance to get the disease. So then your population size. Okay, so if we do that, so of course this implementation we're already including the false positive rate 95%. Okay, so then, false positive rate 5%. Okay, so that's what we get on the 2 column. Okay, so with disease, okay, so test positive is only 10% because our sample size is 10,000. Okay, so then since they have disease but test negative is 0. But no disease, you test positive is 500. Okay, so from this table we also can see here, according to the test positive, right? So we can using the 10 divided by 510. So that's about 2% as well. So what this result tell us? So in this example, we told you, even you test positive, but it can be wrong. Yeah, even you are healthy, okay, but you have so many people is healthy, then you go to do the test. The test do have like 5% error. Okay, so then we find out even you don't have disease, but you test positive, we have 500 people do that. So this one actually tells us one thing is, be careful in this question beginning we told you, all those people don't have symptoms or a sign. Then you try to ask them to do the testing. But on the other hand, that's meaningless because the test itself has the error. If we don't have any symptom, we just grab a bunch of people to do that. Okay, so sometimes you have a lot of is the false alarm. So most of the time it's like COVID. This kind of test, we will have the people has the symptoms, then we do the testing. But something else like the breast cancer or those annually check, then even you don't have symptom, right? Even we have the error, you should go to check because we want to get that to prevent that happen. But for some tests, if we have using the symptom to know better, that will be better after you have symptom, then you do the testing. So we will see more example in the next video. But here we show you the base rule example and got the answer about the people has disease and test positive.